Hello everyone. So in the last lecture we have discussed about attenuation of shock wave. This lecture we will focus on interaction and reflection of shock waves. So we will discuss about how what happens when a shock wave enters from one medium to the other medium, and also what happens when it reflects from a free surface, or what happens when two shock waves interact with each other. So first we will see when a shock wave enters from one medium to the other medium. Let's say we have a medium A and this is the interface and this is the medium B. So what will happen when the shock wave enters from one medium to the other medium? The pressure, shock wave velocity, density, so these parameters will change in the other medium. So if we write P1 US1 rho 1 in this medium, so here it will be P2 US2 rho 2. The shock impedance concept we will here introduce. Shock impedance is rho naught US, like our sonic impedance. So this is shock impedance of a medium. So this shock impedance gives a measure of pressure at a particular particle velocity, at a particular UP value, and this can be approximated as rho naught C naught. We can approximate at rho naught C naught. C naught is the, as we know, sonic wave velocity. Sonic wave velocity, and then rho naught is the initial density. So this is, we know that initial density of the medium. So in these problems from transmission of shock waves from one medium to the other medium, so we will be using shock impedance matching method. So impedance matching technique will be useful to calculate the shock transfer from one medium to the other medium. So this is the method, the graphical method we will be working on. So now we will discuss two cases. Case number one is transmission of shock waves from low impedance medium to high impedance medium. Transmission of shock waves from low impedance. Let's say we assume that we name them that as A to from A and to a high impedance medium. High impedance, sorry, high impedance medium, or you can call high impedance material. So for this case, what we can do is, for this problem we can first draw a pressure particle velocity plot. So this is y axis is pressure and x axis is particle velocity. So we have two mediums as we have written here, the low impedance medium, the PUP plot from the experimental data. So this is, let's say, medium 1, and that we know that the shock impedance rho naught US will be the slope of the line at a particular pressure. So what we told that that's the shock impedance is a measure of the pressure at a particular velocity up. So if you have this pressure P1, if you have a pressure P1, so the shock impedance of this material A will this slope of this dotted line, so this will be, the slope will be rho naught US, that is the shock impedance of the material A. So if you draw the curve for the high impedance medium, higher impedance medium, so this will look like this. This is high impedance medium with a higher slope shock impedance. So now we will draw the reflected wave. That should be a mirror image of the curve A, because the reflected wave will be exactly opposite, it will follow the opposite path, that means the variation of pressure and particle velocity will be a kind of mirror image to what we got for the curve A. So how we can draw is, we will draw the curve like this, although it's not perfect. I hope you can understand this. So this curve, the curve A, and curve this one, we will name them that as a AR. So that should be kind of mirror image, approximately a mirror image, and it will cross the curve B, and that point will be corresponding to P2, that is the pressure of at medium B. AR is, as you know, the curve for reflected wave, reflected at the interface of medium A and B. This is for medium A, this curve, and this curve is for medium B, or we can write material B. So if we draw the pressure profile or stress profile, so we will now draw the pressure or stress profile of this transmission of wave. So what we can do is, at time t naught, let's say we have I am writing this vertical dotted line, which is the impact interface. At time t naught, pressure pulse is, this is the shock pulse, it has a steep shock front, and the pressure will be P1. So this is the shock wave. This, actually we should write that this is material 1 or medium A, and other side of the interface, this is material B, or we can write medium B. So what will happen after some time, at time equal to T1, this shock pulse will hit the interface, and then at, let's say, time T2, so what will happen is the pressure will increase. As we can see here, it was still P1, and here we have the pressure will little increase. As you can see from our PUP plot, the pressure will be P2 now. So here, if you can see from the above diagram, this pressure here is P2. So here it is P2, and then the original pulse will still be at P1. So this is at P1, and it is important to note that the release wave, we discussed in the earlier lectures about the release wave. So this release wave will still travel towards the impact interface. So this is, I will write it somewhere, this is the release wave, I will write it somewhere here, release wave, this one is the release wave. And so at time t3, what will happen is this wave, so better we will again redraw this part a little bit. So why I have redrawn, because I did not show the reflected wave from the interface here, so that I will show you. So this, there will be a wave which will reflect back from the interface, and that will also maintain a pressure P2. So that reflected wave reflected back from the interface of the low and high impedance medium, so that will interact with the release wave which I have shown earlier. So both of them are actually, we can call them a release wave, but the first one is the release wave, this one is the release wave of the primary wave, and the second one, this which is traveling from right to left, is a release wave. I will just show with an arrow here. So this is the release wave that is reflected back from interface, Now what will happen, these two waves will interact, the release wave from the primary wave and the release wave from this the reflected from the back surface, they will interfere, and then this will now look like this with a pressure P2. So now after some time, the T4, when this will meet, so in this case the both the release waves meet each other, or both release waves meet each other, the result is, we can see at time t equal to T4, this will move forward in the medium B, and so this, the release waves will move from left to right, and then part of the other wave, this is the result of the interaction between both the release waves, so which is P2 minus P1. The P2 minus P1 is the pressure of this part of the wave, and the other part is still at pressure P2. So this is results from the pressure decrease, which is from P2 to this P2 minus P1. It's a results due to interaction of the two release waves. So as you know, one is release wave of the primary wave, and the other one is the release wave of the reflected wave back from the interface. So it is important to mention here that there is a continuity of pressure at the interface, so that we can see at time t equal to T2. So if you see the interface in this point, we can show that continuity of pressure at interface. That means the pressure will be P2 on both sides. Both sides of the interface. So that continuity will be maintained. So now we will discuss about the case number 2, which is the opposite case, that is transmission of shock wave from a lower impedance medium to a higher from higher impedance medium to a lower impedance medium. So we will see what happens in that case. Transmission of shock wave from high to low impedance material. Okay. So in that case, so if you want to draw a PUP diagram, pressure particle velocity diagram. So let's draw the medium A, which is a high impedance, has a high impedance, and then we have a medium B which has low impedance. So now if we have a reflected wave curve which will be a mirror image of the curve at for the medium A. So this is, let's say, AR, that reflected wave, and then let's say this is at pressure P1 in the medium A, and because the AR curve will cut the B curve at a point, at this point, so the pressure at the medium B will be P2. I am repeating again, this curve AR is an mirror image of the curve A, and it cuts the curve B at point which is corresponding to pressure P2. And if we can have this particle velocities, this is, we can say that this is UP2 and this is UP1. In the previous case, sorry, I did not mention, I think these particle velocities are, I forgot to mention here. So this is UP1 and UP2 are the two mediums, the particle velocity values here. So now in this case, so if we want to draw the pressure stress or pressure profile, so what we have drawn now is PUP plot, pressure UP plot, this one, and then if you want to have a pressure profile or stress profile, you can call it a stress profile as well. So what will happen is, we can take this as the interface, that is the interface, as you can see from PUP plot, this is the interface. We'll continue like this. At time equal to T naught, so the pressure pulse, the shock wave pulse, is moving towards the interface. So we have left side is medium A or material A, and the right side is material B or medium B, and at time equal to T1, this pulse will hit the interface. So we can write even here that pulse hits the interface, and then T equal to T2. So what will happen here is, at pulse at time T equal to T2, what will happen is, this pressure on side B or material B will be less. As you know, this pressure will be P2. Earlier it was P1, which is higher than P2, and in this side in this side, which should be actually smaller here, and this side it will look like this. So what will happen here is this part of the pulse will come towards the left side, and the release wave is traveling towards the right side. So you can see at the interface, this interface, there is a pressure continuity at the interface, pressure continuity at the interface. That means pressure is P2 on both the sides, and this pressure is P1, the higher pressure, and this is at interface, P2 at interface on both sides. So that is the pressure continuity. And as you can see, these two waves, which is, that means from this is the reflected wave from the interface, that you can see it doesn't have a stiff front, so that is actually not exactly a shock wave, it has an inclined front, and the release wave of the primary wave, which is traveling from left to right, and these inclined front is traveling from right to left. So these will interact. So what will happen, this will, when it will interact, it will form a tension. So it will form, when these waves will interact, it will form a tensile wave. So at this point it will have a tensile wave, so that is why I am drawing below that reference line. So this will be tensile wave, and that tensile wave will be at time t4, this will propagate. What will happen is, so we have the pressure P2, we should not have drawn the pressure P2 in the front, it should be showing at the pressure level, or we cannot, I think we'll cut this here. So that tensile pressure, tensile pulse will propagate at the material A. So that tensile pulse or that tension can lead to spalling if the amplitude is sufficiently high. Sufficiently high. So that we can see now. So what happened in this second case? The first case we did not see a tension behavior or spalling kind of behavior. In this case what happened, transmission from shock wave from higher impedance material, that is A, to a lower impedance material, that is B. So it shows that when the release wave from the interface interacts with the release wave of the primary wave, that can interact to form a tension, and that tension tensile wave, if sufficiently high amplitude, can cause spalling, that means it can lead to failure. So we will quickly see a problem involving this wave transmission from one medium to the other medium. Let's assume this, we need to, the problem is, let's say we need to calculate the pressure generated when a, let's say some 50 gigapascal pressure pulse is traveling from material A to material B. So what will happen here is we have a material B and material A. So we will consider both the case. First case is, let's say, from A to B, and in the second case we will assume the other case. Let's say second case is from B to A, and this is the interface. This is the interface. So we can draw the PUP diagram, that is pressure particle velocity diagram, from experimental data. UP diagram, PUP. So what we can do is we can have these curves. Let's say this is curve A and this is curve B. When the material travels in the case A from A to B, let's say we will draw a curve which is mirror image of A. We'll draw a curve mirror image of A. It's something like this, mirror image, these two, this one and the other one, although my diagrams are not very perfect, but you can assume it to be mirror image. So that means these this is the first case, which is from A to B transmission, and this is the reflected wave. So in that case, what happened, the pressure which was 50 gigapascal now cuts the medium. This curve, reflected wave curve, cuts the medium at this point. Let's assume that this is 30 gigapascal. So what will happen is the pressure which is initially at 50 gigapascal here will be now in the medium, it will be 30 gigapascal. In the other case, what we can do is we can draw the reflected curve as something like this. So it will be, reflected curve will be mirror image of B. We will draw a mirror image of B. So the mirror image of B is this reflected curve, or we can even name both of them. What we can do is, let's say we can reflect it first. For the first case, we can give the reflect AR as name, and this is, let's say we can give BR as the name. So now what will happen, this is the second case from B to A. So that pressure should be same 50 gigapascal. Sorry, this is a little bit higher. This should have been at 50 gigapascal. So what will happen is this reflected curve will cut through this A curve at this point, and this pressure, let's say this pressure is something like 75 gigapascal. Now what happens, so this, in this case, if you have a 50 gigapascal pressure from medium B which is entering medium A, then pressure will increase because it is the 75 gigapascal at low impedance. This one is low impedance, and then medium A has high impedance. So in the same figure we can show both the transmissions from medium A to B and B to A. So now I think it is clear from this problem. Then we will talk about superposition of two waves, that is interaction of two waves. So what will happen, two shock waves interact with each other. Let's assume at time t equal to t naught, we have two shock waves approaching each other, and we can have, the pressure is P1, and when we will encounter each other, this will be look like something like this. So these two are release wave, and after interacting it will this will reflect back. So at time t2, this wave will look like this, and then at time t3 this will be separated, and this will, both the waves will go back away from each other. This is at time t3. So what we can do in this case, this is actually what we are talking about, the collision of two shock waves, and we can see they have shock waves, they have parallel fronts, that you can see these fronts are parallel to each other. So now what we can do is we need to find the pressure P2. How we can find the pressure P2? We need to add the particle velocity of both the waves. Let's assume both have same particle velocity. Then we will add the particle velocity of both the waves, and then correspondingly we will obtain the equivalent pressure, which is the corresponding to the addition of both the particle velocity. So let's make it clear from this PUP diagram. So we have this PUP plot, and let's assume this as UP1 at pressure P1. So pressure P1, particle velocity UP1, and we assume that the two waves have same velocity. So this wave and this wave has same particle velocity, same UP. So what will happen is, then the UP of this the resultant wave, the superposition of two shock waves, okay. So when it superimpose, so what will happen if they have both same UP? So we can write the, at superposition we have a value twice UP1, and correspondingly what is the pressure, we will find it out. That is, in this case, let's say P2, and that's what so then we can find that the pressure after superposition is P2. So that's how we can calculate, but we should understand that P2 is not equal to twice P1, but UP2, which is this one, UP2 is equal to twice UP1. So, and we use this equivalent pressure P2 from this plot. So again I am repeating, we should not be confused that the P2 is equal to 2P1. It is actually not equal to 2P1. So it is from the particle velocity addition we can find the equivalent pressure. Now we will talk about reflection of shock wave at free surface. So this is, as we can understand from the earlier elastic wave calculations as well. So this is a special case of transmission of shock wave from material A to B, material A to material B, and we assume that the shock impedance of material B is 0. Shock impedance of B is 0. So that's a special case. Similarly, we did it for elastic wave propagation. So in this reflection of shock wave, we can consider two cases. First case is a square pulse, and second case is triangular pulse. So we will first talk about the square pulse. So to understand this, so what we will do is, to understand this reflection of shock wave at a free surface, what we can do is we can draw a PUP diagram, and then we have this curve for material A is this one, and then curve for material B is the horizontal line, which is exactly the x-axis. So that line is our line curve for B, material B, and if you draw a mirror image of A, which is the reflected wave, so that is is a mirror image, so that we will write as AR, that at medium A the pressure is P1, and the corresponding particle velocity is UP1. So as it is a mirror image, AR is a mirror image of A, so this reflected curve will cut the curve B at UP2, or we can write twice UP1 because of the symmetry of the AR and R curve. So AR curve will cut through the curve B at twice UP1. So if you draw the pressure profile, what will happen is, you have the free surface. I will write a vertical line, free surface. This one is the free surface. So at time t naught, this pressure pulse will travel towards the free surface. At time t1, the pressure pulse will hit the free surface, and you know that we have a release wave following the primary wave, and then this release wave will interact now with the reflected wave, because at time t2 the wave will reflect back. So what we can see is here, the wave will reflect back, that is also release wave from the free surface, and then release wave of the primary wave is from left to right hand side, and then this will come towards each other, and at time t equal to t3, so what will happen, it will generate a tensile wave. Because of the interaction of both the release waves, it will have a tensile wave. So this is tension, and these tension can lead to spalling. If the amplitude is quite high, sufficiently high, then it can lead to spalling. Or very quickly we can show the particle velocity. If we draw the particle velocity profile here, so what we can show is at time, so if you have the free surface, and at time t naught, this the particle velocity profile will look like this, and then at time t equal to t1, the particle velocity when it
hits the free surface, let's say this is UP profile, and then particle velocity at t equal to t2. As you know, this will be now it's a high velocity UP here and twice UP here, because from this we can see that this is from PUP plot, this is twice UP, and so this will the reflected wave, both the release wave will interact, and at time t3, so we'll get the result of this interaction. So this is time t3. So basically this will reflection at the free surface we can cause spalling if the tension has sufficiently high amplitude.
Thank you.